I don't like dishes at all. Testing. Bad experience as a 10-year-old boy.
You get both of
No, I live in Sacramento, and my friend's dad did all the feeding of the horses at Cal Expo, where the state fairs held. And they do horse races. And he took us one time. He used to get us into the fair all the time for free, going into the stables. But he took us to the stables one time and took us riding. And I was sitting in front of him on the saddle, and it was chafing me. The fucking saddle was chafing me, and I wanted off. And he wouldn't let me off. We fucking rode like another 10 minutes. I could barely fucking walk after that, and I held the grudge against the fucking horse, not the fucking old drunk white guy that was fucking riding me around. Since then, it's like, nope, fuck you horses. All right, we're doing 4.3 and 4.4 today. 4.3 is on logarithms in general. And in 4.4, we're gonna go to the fan favorites of logarithms and change base formula. Now recall that we started this chapter. What was 4.1 on? 4.1 was on inverse functions. And 4.2 was on exponential functions. So this is where we swapped y and x to find the inverse. And this was on y equals e to the x. Or a to the x. Say a to the x. E to the x is a specific one. That's one of the fan faves we're going to hit later on. Let's combine these two. We already saw, I decided to teach this a new way just today. We already saw that y equals a to the x goes like this. That's a one-to-one function, isn't it? This function is one-to-one. Which means like if I called this f of x equals a to the x, then f inverse exists. And so we'll do that. F inverse, we swap x and y. I've got x equals a to the y. Which is a little weird. This says x or the output is the value that a must be raised to in order to have the input. That's some crazy shit. When we did the F inverse though, the next step always was to solve for y and replace with F inverse. But y is in the exponent. So mathematicians had to come up with a way to get it out of the exponent. This is where logarithms come in. X equals a to the y is equivalent to y equals log base a of x. This is referred to as base a. Really memorizing this thing is like clutch to everything else in this entire chapter. Remembering this, and it's a pain in the ass. It really is. I even to this day have to stop and think about it. And the only way I remember it easily is this is the base for the log. This is the base of the exponent. And they are the same. A is the base for both of them. And my variable that's touching it switches. Leave that up and look at some examples. I can do a little table. Let's look at log form and exponential form. If I had 3 to the 4th equals 81. The equivalent over here in log form is the exponent is the thing that goes off on its own. The base of the logarithm is the base of the exponent. And that goes there. Some calculators nowadays do have a button that says log AB. Not all calculators do. We will address this with the change of base or calculators that don't. And we can go the other way. We could start with log 1/2, log base 1/2 of 8 equals -3. I want to go the other way. The base is the base of the exponent. The value on the other side is the exponent. And whatever the argument is of the logarithm goes by itself. Let me give you guys something to try. Try converting it into the other form. Yeah,
What's the next to 25?
that is 1/125.
Oh, what's
Yeah, it looks like it, yeah. It was sloppy handwriting, and I almost did it again. I apparently like to write the fucking fraction line too close to the one. Starts looking like a perpendicular. And then when I got one on the bottom, now it's like a fucking plus sign, because I'm a champion like that. Give me one more minute and we'll do them together. We're almost done. Almost. Almost, folks. Hang in there. It's our final. Finals on May 16th. How many days away is that? That's 4 weeks. You'll be done in 4 weeks. Woohoo! On to phase 2, trigonometry. Yeah,
when's the last day of this?
May 16th is technically the last day of class. And we could do more stuff on it, but I figured most of you have finals. Finals are technically the week after that. I decided to do the final a day before, so that way you guys don't have them all at once. But the actual last day of class is Thursday, May 18th. Which is when finals would normally be. I guess I didn't move it that much up, did I? It's only 2 days before. But I will be here on May 18th, on the Thursday on May 18th, presumably with all your shit graded. So you'll be able to come by and take a look at your test and see how you did, if you're curious. Is anyone taking Trig over summer?
I am.
Nice. Is anyone trying to get into my calc class next semester?
I'm already in your calc class for next semester.
I haven't looked at the roster. Cool. Can't do Trig for you over the summer, but I do have Trig videos up on YouTube if you don't like whoever's you're with. All right, so what can I do with this 10 cubed equals 1,000?
Log base 10,000.
Did anyone else get that? Yeah, this is the base for the log. The exponent ends up being the other side, and the value that equals is the argument. What about this one? With my super giant plus sign.
5 to the -3 power equals 1/1.
That's correct. What about this one?
Base 12 of 12.
You're the only one answering. Isn't that fun? Okay. Anyone else want to try? Yeah. All right, so I had said they were inverses of each other. Let's just sketch them. I'm going to draw in that y equals x line because inverses are mirrors of each other over the y equals x line. We had y equals a to the x there. And y equals log base a of x here. Good to know. A lot of the same ways we were able to shift y equals a to the x to graph of it, we're going to be able to do with log as well. But let's take a look at doing some solving of log problems where there's actually a variable in it. This part was easy to do because you could plug them in a calculator and find out. Give you all a chance to write that down. Let's say we had log base x of 16/9 equals -2. We're going to apply what we're learning and rewrite this as the other form. My base is the base of the log, the base of the exponent is x. The other side is the exponent. And the argument of the log is that. Ideally, we can rewrite this as something to the -2 power. And if we can, then we know whatever this is x. So maybe the better way of doing it would be writing it as just to the positive power. This is 4 squared over 3 squared, or 4/3 squared. Yeah, sorry. And then we can flip that thing. Flip 4/3, we get 3/4. And that'll be to the -2. And that shows us that x equals 3/4. And that x could be in any of the spots. Very rarely is it the right side, but sometimes it is. Let's look at another form we'll see. Maybe the x is the argument. That's a really big number. That's not what I want there. Let's put like 3/4 here. Now, when I rewrite this, the 16 goes together. The 3/4 is the exponent on it, and that equals x. So what can I rewrite 16 as? Sixteen is 4 squared, right? I could do 4 squared to the 3/4. Can I break down the 4s anymore? I can, right? Each of the 4s is a 2 squared. So 2 squared squared to the 3/4. That still equals x. So this is like 2 to the 4th times 3/4 ends up being 2 cubed, which is x. 2 equals 8. You'll notice solving these is a lot of just number manipulation, right? Other than remembering how it transitions from one formula to the rest, a lot of this is just number manipulation. If I rewrite this, this is 36 to the x equals square root of 6. A square root of 6, though, is 6 to the 1/2. So that might be a more helpful form in figuring out what x needs to be. So I can't really do anything with the 6 to the 1/2, but I can rewrite 36 as 6 squared. And using our rules of exponents, this turns into 6 to the 2x equals 6 to the 1/2. The bases match, meaning the exponents have to match. So we end up with x equals 1/4. Now, those are the different ways we can use those formulas. Let's go back and look at that function log base a of x. And how that is the same thing as x equals a to the y. One thing we can note is x has got to be greater than 0 from the graph. So that's my domain restriction. And that correlates to the range of the exponential functions. Range on exponentials was y was greater than 0. What happens if we have a be a negative number? Let's say a is like -2. Let's just see what happens when I stick in values of for y. If I put in 0, I get -2 to the 0 is 1. If I stick in y equals 1, I get -2. I stick in y equals 2, I get -2 squared is 4. If I stick in -1, I get -1/2. If I stick in -2, I get positive 1/4. Let's just look at what happens when we graph that. Yeah, 1, 0 is here. -2, 1 is here. 4, 2 is here. -1/2, -1 is down here. And 1/4, -2 is down here. It's doing some weird shit, right? It's not making the graph we know. This is not giving me that. And the reason why is where the restriction on a comes in. We require for the exponential functions A needs to be greater than 0 and A is not 1. When A equals 1, you just have 1 repeatedly. It's a straight line. And that matches the restrictions. We have the same restrictions on exponentials. I've done the graph word a couple times. Let's look at how you can just sketch it real quick and what to do with translations. That's just plugging in values for y and seeing what x equals after I do. The most important ones to remember are these three. Because after that, you're going to kind of just freehand it from there. Remember these. Now, what do we have here? We mentioned some of this. X has to be greater than 0. That's my domain restriction. Y is in negative infinity to infinity, or all real numbers. That's our range. And this picture in specific is when A is greater than 1 for this graph. It is increasing on its entire domain. Y equals 0 is a vertical asymptote. When A is between 0 and 1, this actually flips upside down. When I stick in 1, I've got 1 over A. And when I stick in -1, I've got A.
Could you scooch it down a teeny tiny bit?
Yeah, I got it.
Thank you.
I think I have that backwards. Let's see. X equals A to the Y. When A is 0, that's still 1. When A is Y is 1, it's A to the 1, but A is a fraction. So this is like 1 over A. That's not really 1 over A though, that's not a good analogy. But yeah, that is what it is. That's what I got listed over here. What am I tripping out on? A. The graph ends up going upside. I don't know. Maybe I need to picture draw it. I'm fucking myself up with the XY table. So that's 1. This is A, and that's -1. Yeah. And that's 1, and this is like 1 over A. So, same setup on the domain and range. Everything is the same except this version is decreasing everywhere. Ready for some more? So we look at graphing specific ones. Like if I have log base, y equals log base 5 of x. And this is the same thing as x equals, not x equals, y, or yeah, x equals 5 to the y. I'm gonna say that's 5 right there. Nope, we'll say that's 1. When y equals 0, x equals 1. When y equals 1, x equals 5. And when y equals -1, x equals 1/5. If we went up to y equals 2, this would be all the way over at x equals 25. And we can take a look at when the base is less than 1, but still greater than 0. Log of 1/3 x. This is like saying x equals 1/3 to the y. Which is also the same thing as 3 to the negative y. So we'll have some action at 3. Again, crosses at 1, 0 every time. When I do y equals 1, x equals 1/3. And when I do y equals -1, I get 3 to the -1 is 3. So the graph's doing something like that. The shifts work like normal. If we have something like f of x equals log base 2 of x minus 3 plus 2. You sketch log base 2 of x and then shift it right 3 and up 2. Just like we've done with everything that ever had f of x minus h plus k. It shifts it by hk. All right, you guys ready? We've got a couple properties. I'm going to prove the first one. They're all derived the same way. I'll show you how we get the first one. Let's say I have log base A of x equals m. And I have log base A of y equals n. This is kind of like saying a to the m equals x. And a to the n equals y. That's our starting information. What I'm going to do is I'm going to multiply these together. I'm going to do x times y. X times y equals a to the m times a to the n. And that means I could rewrite that as a to the m plus n. Let's use our log rules and go the other direction. Let's rewrite this in the form of the log equation. So I'm going to do log base A of the xy equals the x number. But I have m and n already up here as logarithms. Log base A of xy is equal to the log base A of x plus the log base A of y. That's our first property. Other properties. Let's call that A. B is one with division. And where multiplication turns into addition, division turns into subtraction. We've already seen this in one of the examples. Log base A of 1 equals 0. And we've already seen D. Log base A of A equals 1. We did this with the 12 and the 12 just a little while ago. And those one like C and D, if you just rewrite them in the other form, it kind of falls out directly from it. And there's no work involved in finding C or D. The one that's a little more non-intuitive is that if I have log base A and I've got x to the r, the r can come out front r times log base a of x. This is called the power property. And it's really helpful. I think the easiest way to see that one is, I'm gonna put a box around it. But seeing it in action. If I have log a x cubed. This is like log a of x times x times x. And we apply the first rule. This turns into log a of x plus log a of x plus log a of x. And when you add those all up, you have 3 times log ax. And notice our property, our exponent is now down in front. So kind of, it's a fallout of the addition one, the product one. You guys ready to do some examples? Here we're just practicing manipulating them. If I have log base 7 of 8 times 6. It's multiplication, so I could split it up. You do log base 7 of 8 plus log base 7 of 6. Log base 2 of 6 over 5. Division turns into subtraction. Log base 2 of 6 minus log base 2 of 5. What about log base 2 of the cube root of 9? So here it might be easier to rewrite that cube root as an exponent. And then I can pull the 1/3 out front. give you guys one to do. So what do we get here?
Read this log base A.
It's correct. Anyone else get that? Yeah, the hard part here is rewriting that as R to the 3/5. Remembering your rules with radicals. We can have really, major clusterfuck one. Messy, right? We got 5 different variables, so we should be able to end up with 5 different logarithms. We have a log base R, A of R. And we got one with an S, but it's squared. We can pull the 2 down in front. And we have T by itself and it's multiplied on top. So we just do log base A of T. Interesting way to approach this. You could also look at this as RS squared T U to the -3, B to the -5. and just do the multiplication rule with the power rule the whole way. Or you can recognize that we are dividing it, so this is subtraction, and 3 can be moved down in front. Same thing with the V, but the 5 can be moved down in front. Any questions? Come on, you were first.
So when you have exponents, they always follow.
Yes. Well, you don't have to put them in front, but they're much easier to work with usually.
When writing out that answer, or with the -3 log a to u, would that come after the log base a of t?
It can actually, with addition and subtraction, you can put it in any order, because as long as you keep the minus with the right things.
So it doesn't matter where it goes.
Correct. I could have started off with -3 log AU, and then I could have said log AR, and then I could have jumped over to the T. And then I could have gone back to the V. And then I could have just went and did the S. Either of those work. The reason why I kept them in the order I had them is because R, S, T, U, and V are in alphabetical order now. The bases are all the same. So I kept them in alphabetical order.
You know, if the bases were different,
If the bases were different, we couldn't put them together like this. This requires that. It's a good question. Bases always need to be the same. Let's do some practice going the other way. Let's say you start off with log base 4 of x. And you subtracted log base 4 of y. And you added log base 4 of z. What can I rewrite this as?
log base 4 of x times z over y.
X times z over y. Yeah. I think this actually helps answer the question you had just asked too. If you were to go forward this way, and we kept with the order we were doing with the positive everything on top first, we would have done the x and the z first and then the y last. And I know, but you didn't say x over y times z. You said x times z over y, which means you put it like that. What about 4 log base b of r minus 5 log base b of s? Yeah, this guy used 5 and s on the same fucking thing. That was smart. Hey, let's change that to a fucking t. T's don't look like 5s. You get here. Yep. Ah, that's too easy. Let's make it harder. Enough of this easy mode shit. This might be easier to not try to jump to the end. Just move those up as exponents for now. So I put these together. Right? Another way of looking at is if we look at the exponent, the 3 on bottom says that's a cube root. And then I've got x to the first power, y to the second power. I don't know if I'd do that though. I would probably work with these right here and simplify this. This is log base a of 1 over x to the 2/3, y to the 1/3. Or we could have them with negative exponents. Point is, there's a lot of manipulating we can do with it.
Except the exponents.
Yeah. A useful thing. And it stems from the rules we had about inverses. Recall if we stuck an inverse inside, oops. If we put one inside the other. Or if I put f inside of f of x, or f inverse, both of these end up getting me x. Let's apply that to what we know with logarithms. F of x equals a to the x, and f inverse of x is log base a of x. One of these isn't as helpful as the others. If I put f of x inside f inverse, I'm really putting in a to the x. And I get log base a to the x. We already talked about powers can come down. And when the base matches the argument, this is 1. So this is just x. That's not as handy to memorize, but it's got some value. There you can apply just the power rule, bring the exponent down, and it's simple. The one that's really helpful is when we go the other way. When I have f and I put in f inverse in the orders I have here. So if I have a and I put in log base a of x, this has to equal x. Because when you put an inverse inside of its other opposite, you get x. This is a handy formula to memorize. You will do this, let's see. I don't know that you're going to do it in calculus that much. You might have it some in calculus. It's all over differential equations. Yeah, you'll have it. Now, it's a differential equation. Stop it. It shows up again and again now. So if you have log base a and it's in the exponent, they kind of just cancel each other out. That's the way I remember it. Base a with log a in the exponent. Cancels out, and we're just left with the argument of the log. All right, that was 4.3. It's long. 4.4 is fucking quick. Because you learn all the rules of logarithms now. Now we're going to talk about fan fades of logarithms. 4.4 is on the common ones. And change of base. Our number system, the one we use, the one we love and use, is base 10. That's a common base. Log base 10 of x, where a is 10. This is a common base. And when you had, what you will see is log x. If the base is not listed, or log, it's base 10. So those two mean the same thing. It's kind of like when we have like x to the first power, we don't say the first power. If the 1 is the default setting, base 10 is the default setting for logarithms. It's how our scientific notation works. If we had 391,200, we could say this is 3.912 times 10 to the 5th. We use 10 as a base in a lot of our operations. And so, since this is the way our number systems work, when you do a log graph with it, it makes it look a lot easier rather than having to go out to 10,000 to cover 10 to the 5th. You're only going to 5. That's pretty fucking helpful. You can fit everything you want in like a small area on a graph. Rather than going to 10,000, we're going to, or 100,000, we're only going to 5 steps away. The problem with log graphs is very rarely are they labeled really well that this is a log graph. And then they're hard to like get, you have to think about what it means. So this is a common base. And this is a calculator button. Calc button. The other calculator button is ln x. And it means log base e. So maybe that says calculator but or calculator buttons. There we go. Log x and ln of x. So if you wanted to find values for these on a calculator, they're really quick. You don't need that log base A of B button. Some calculators have log base A of B, and you have to, some calculators have this too. For those that don't, we have the change of base formula. The best way to call this. We have log base A of x. Can be written as log base B of x over log base B of A. So you introduce a new base. Where is this really helpful? Your calculator doesn't have log base A, B button. I can turn log base 2 of 7 into log base 10 of 7 over log base 10 of 2, which is just log 7 over log 2. Alternatively, I could use E here for each of these, and I could have ln of 7 over ln of 2. ln stands for natural log. Apologies. Take one of the Costco's got some sort of fucking allergy pill that works really well for me.
I've tried several things.
Now, if I was in Sacramento, I'd be fucking dead. I think for some reason, I'm more allergic to the shit in the air in Sacramento than I am here. And I grew up in Sacramento, so I was like a fucking red little beach ball all so fucking spring. All swollen up and fucking red when I was a kid. Get the fuck out of that town. Here it's a little bit better. I'm still allergic to a lot of stuff. All right, so natural log or base E shows up a lot in nature. It shows up even in business shit. Continuously compounded interest is base E exponent. And you will find out that e to the x is going to be your favorite fucking function when you take calculus. Because in calculus, one of the first things you learn is, well, one of the main things you learn all semester is how to find derivatives. And the derivative of e to the x is e to the x. It does not change under the derivative function, derivative operation, which is the only one that doesn't. Everything else changes. 2 to the x changes. 10 to the x changes, e to the x does not. Parabolas change, sine waves change, everything you've got changes except e to the x. In fact, there was a fun meme going around with the Super Mario Brothers movie with do you yield? And Bowser going, I do not. I wonder if I can find it. It's lame. But man. I'll have to find it later and show it to you on Thursday. Where do we use these kind of things? Where does log and shit come from? Like our so applications. Real quickly before we tap out. Chemistry, our pH system. pH of a solution. pH is the negative log of H3O plus molecules. Sorry, hydronium ion constant. This is hydronium ion concentration. It's not molecules. It's in moles per liter. That's some chemistry shit right there for you. You're going to use a mole for a term. A mole is an animal.
That's the worst.
Chemistry's got a lot of memorization in it. It's got a lot of algebra in it, believe it or not. It really does. So if algebra is not your strongest, then yeah. Pure water has a pH of 7.0. If the pH is less than 7.0, it's considered acidic. And if it's greater than 7.0, it's considered basic or alkaline. Yeah, basic. We usually round to the 10th for pH. So if we have that there is this many H3O plus molecules, 6.8 times 10 to the negative 8. The pH is the negative log of that. We already showed we can break that up because it's a multiplication, so we can turn it into addition. This is log base 10 of 10 right here with an exponent. This all turns into the negative stays out front and the negative 8 comes down. So we have a plus 8 from that one. This value, when you throw it in a calculator, you get about negative 0.8325. And so when you add this all up and you round to one decimal place, the pH is approximately 7.2. So slightly alkaline. In physics, when you measure this level of sound, decimal ranges is another operation that uses the logarithm scale. This is measured in decibels. We usually have the decibel is D is 10 times log of I over IO, where IO is the intensity of the faintest sound that you can hear. The most faint sound. Or some sound threshold. And I is the intensity of the noise that you're listening to. Let's see, jet engine decibels. For a jet engine. D is usually 160 decibels. We use dB as decimal, sorry. Human ears rupture at 150 decibels. That's why they gotta wear those fucking earmuffs and shit, blocking out those, filtering and dampening out as much sound as they can. When you see like Top Gun movies and there's people that are working on a flight deck, fucking if they didn't have that shit on, they fucking blow up their hearing with the first jet taking off. Now, the way sound works is it drops proportionally to how far you are out from the sound. But an air flight or like a aircraft carrier isn't that big where you're getting far enough away from a jet if you're still on the top of the deck. Especially since it's got to go down the fucking runway to take off. So it doesn't matter how far away you are on it, you're still fairly close to that jet at some point. They have to wear all those things on it. So that's another example of where logarithms come in. Continuously compounding interest. I think it's just e to the RT. Yep. Continuously compounded interest. Interest is A equals PE to the RT, where R is the annual rate. And T is time in years. Remember the one we had where it was P times 1 plus R over N to the NT? That's regularly, so this is regular compound interest. Where N is the times per year, it's compounded. Daily would be 365. So, as you go from daily to hourly to minutely to every second, tick, 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 interest is compounded. It shifts from having this 1 plus R over N to an exponential function, which is crazy. It's crazy. Aging rocks in geology, it does measures argon and potassium. It also uses a logarithm scale, a natural log scale. There's a lot of different things when you're going through the sciences and stuff where the log functions actually show up. Modeling diversity of populations, things like this. There are examples all over the place. Let's just, yeah.
Also, if I'm not mistaken, I believe the new way of, I mean, not the new way, but the older way of measuring the intensity of earthquake also.
The Richter scale?
Hey, oh, maybe not. I don't know, there is something other than the half-lives with you.
Richter scale is logarithm. Yes, it is. Well done. The magnitude of a, okay, that I should have known that. Just by the way, the fucking magnitude system worked. A fucking earthquake of magnitude 7 is 10 times more strong than the magnitude of 6, which is 100 times more strong than a magnitude of 5. So like going up 1 on the Richter scale sounds like a really low increase, but that's like what okay, so the Richter scale is a perfect example of the log scale. Have a good graph of Richter scales. Let's see. So normally, if you wanted to show something like how much damage it does, like the earthquake that takes down San Francisco is really high. The one that shakes your shit on the just shakes shit on your fireplace but knocks nothing down, that's like here, way down low value. When you can, this is like a regular graph. Probably even lower. Probably like the fireplace is way down there. Because I can't make the San Francisco, like the one that tore down San Francisco in like the 1800s or 1900s, it fucking floored the place. It was fairly strong. When you convert it to a log graph, let's see, what is a we wrecked people earthquake?
The one in Turkey that just happened.
That's a good example. Let me look up the Turkey earthquake. .8 on log graph. 7.8 is like here. This is okay. This is Turkey. On a regular graph, that is 7.8. So it's times 10 to the 7.8, which is almost 8 zeros, almost times 100 million. Okay. So like if I wanted to do something that had like a really low value, and I wanted to do something that was on the Turkey scale up at 7.8, the graph, the y-axis has to be like 100 million long. Like that's really long, right? I can't even conceive even like 100 million inches. I don't even know how long that is. But I can figure it out. I bet it's a hell of a lot longer than I can fucking even conceive. Now, when we convert it down to here, Turkey is at 7.8. And something that barely felt is 1. Even 2 to 3 is still, it's felt slightly, but does no damage. No building damage.
Getting it done, huh?
That's how quickly it escalates. Even a 3 to 3.9, it's more noticeable shaking. Sometimes it causes building damage, but rarely. Like you need a structurally unsound building for it to cause damage. Yeah, some shit like that. And now you move up to 7.8 and it's fucking leveling places. That kind of illustrates this, how the log scales work. It's very misleading unless you know it's a log scale and you can fucking conceive of what that means. This really means 100,000 times stronger than a 1. And not 100,000, 100 million times stronger than a 1. That's fucking crazy. No, 10 million, because a 1 would be 10 to the first. So 10 to the first is like the shit that doesn't do anything. Like you're like, is there an earthquake? Or was I just like, did I stumble for it? Did my leg like spasm? Did I get a spasm in my leg or something? I had that happen earlier. I was in the chair at home, and I swear it just like kind of like you're sitting on the couch and someone gets up off or sits down on the couch, you feel a little bit of motion. That's the kind of shit that's like a 1. You're not even sure it's really there. And then you get up to like below 8. We're not, and it's leveling places. It's crazy. We didn't do much practice with it, so I want to point out the change of base because I know they will ask you this in homework. Change of base. If you have log base 4 of 20, you can do this as log 20 over log 4, or ln of 20 over ln of 4 in your calculator, and you'll get the same answer. That's all there really is to it. So what if I had log 2 and 0.7? What can I put over here?
0.7.
0.7 over log of 2. If you test these in the calculator, if you do log 20 over 4, this one is about 2.161. And this one should be about negative 0.515. If you do them in a calculator, that way you'll know if you're doing it in your calculator correctly. Other than that, let's call this a rack.
I have a question.
Okay.
For natural log, what is E?
E is a number, it's like 2.71 something.
What does it represent?
It's just the magic number around.
Magic number.
Yeah. It has 2 contexts.
One of those repeating numbers like 5, right?
Yeah. It's not repeating though. It is a number found by Euler. Euler is spelled E-U-L-E-R. And then later on, Bernoulli discovered it. And Bernoulli discovered it with finances. I guess he just found the continuously compounding formula.
Have a good day.
You too. It shows up in the way we write sine and cosine waves together as exponents. We end up using e to the ix and stuff. It's just a value that's found throughout nature as a base for things.
Okay.
I don't know how they found it. They did. That sounds like a fun assignment for you though. Report back to me on Thursday, the history of E. No? I'll catch you later.